When looking in magazines about scientific discoveries, I tend to find that they gloss over the actual method of discovery, instead focusing on what that discovery might mean. This might lead to a lot of confusion down the line to non-technical readers, since they might not know why some discoveries are considered legitimate and others aren't. In order to clarify this, I thought I'd take a minute to talk about the scientific method and what is entailed in making actual discoveries. Our first step is clearly defining our problem. In order to have a good idea of what we want to answer, we have to have a very clear definition of the problem. Research is all well and good, but if we're not researching to any goal, we're basically just wasting our time. For this example, we will use the question, why is the sky blue? The question is pretty straightforward, so we know where we're directing our research. So let's get started. Step 2 is formulating a hypothesis. We do some research into the question, and we think that we have an answer, so we formulate a formal way to say that answer in the form of a hypothesis. This is what we expect our answer to be, after we've done all of our research, but before we've done any actual testing. Let's say we examine the sky, and we think we have come up for an answer with why the sky is blue. Let's say our hypothesis is something along the lines of, the sky is blue because the sun is yellow, and as light passes through space, its wavelength gets shorter, creating a blue appearance when it arrives. We're not sure this is correct, but our research points towards it, so we'll go with it. And now it's time for some experimentation. We play with some prisms, record the length of light at various points, both in space and on Earth, and then compile all the data we've gathered. What we find is that the sun actually produces light of every wavelength, some in more or less quantities. As this light travels through space, they remain at a constant length, but once they collide with the Earth's atmosphere, the shortest ones are scattered, but the longer ones pass through or are absorbed. Since blue is quite short at 450 nanometers, it scatters as it hits the oxygen molecules in our atmosphere. Not exactly what we were expecting, but okay. It's time for us to decide whether or not our hypothesis was correct. As we have seen, it wasn't, but that's okay. Just because we get it wrong the first time doesn't mean we should give up. We create a conclusion that says something like, the hypothesis previously provided was incorrect. Through our experimentation, we have discovered that the sky is blue because blue wavelengths of light, which are around 450 nanometers in length, scatter more readily as they are passing through our atmosphere, which gives the sky the appearance of being blue. We have an answer to our question, and we have scientific data to prove why it is true. Now that we have our answer and have told everyone we know why the sky is blue, we have options. The scientist in us wants to learn more, so we end up asking more questions about our conclusion, which will hopefully lead to more answers down the road. Maybe we want to know why the sky is blue and not violet, so we'll repeat the process and expand our theory to include that as well. Hopefully, this helps explain the process that scientists go through in order to answer their questions in a legitimate manner. By repeating these steps over and over again until they have a solid case with a correct hypothesis and conclusion, scientists can convey accurate information to the public and allow people to build on what they have learned. Thanks for watching, guys, and I hope this helps.